Let us now look at an example of a Boolean expression that is a tautology. So what do? We should just observe that the entries below that expression is all ones. You should not even spot a single zero. Okay, let's see. Our example is going to be P implies P or Q. Now how do I write the truth table of this? First I write down P and then Q, and I now have P or Q. What is P or Q? 0, 1, 1, 1. Correct? This is how the OR works. Now, P implies P or Q. How does this work? Look at the P column, look at the P or Q column. Simply do implication of this with this. So 0 implies 0 is 1. You remember how P A implies B works? 0 implies 1 is 1, 1 implies 1 is 1, 1 implies 1 is 1. And so, I get all ones in this column corresponding to P implies P or Q, and hence this expression, this truth table, this P implies P or Q is a tautology, which means it's always true. So, do we really need to use this truth table to say that this is always true? Not really. P implies P or Q. Let me think about it. When is it not a tautology? When P ends up being 1 and P or Q ends up being 0. That's the only place where an implication can go false. If I can show that this is impossible, that P being 1 and this being 0 is impossible, obviously it's a tautology, isn't it? Think about it. And how do I do that? Let me say P is 1, then this P becomes 1. When this P becomes 1, irrespective of what Q is, P or Q will be 1. So you can never have 1 implies 0 ever, which means this implication will always be true, which means it is a tautology. You see the ingenuity of this argument. I did not write a truth table, but still showed that every entry here will be 1. It can never be 0.